Welcome to The Explainer. I am so thrilled you're tuning in today. We are going to dive straight into a world that is completely invisible to the naked eye, yet it absolutely fundamentally shapes our entire understanding of chemistry, medicine, and environmental science. We're looking at the real CSI-style science of molecular identification. But we aren't just going to talk about the broad strokes here. Instead, we are going to slow down time. We are going to look at the exact, high-speed, chronological micronarrative of what happens to a molecule in the very first microsecond it enters a machine called a mass spectrometer.
So pose this question to yourself for a second. How do you weigh something you can't even see? It's a pretty wild problem, right? When scientists need to identify an unknown environmental pollutant in a water sample, or maybe verify the exact molecular structure of a newly synthesized pharmaceutical drug, they can't exactly just drop it on a tiny scale. Instead, they have to rely on the brutal, fascinating physics of the mass spectrometer. And the craziest part? To weigh these molecules, we actually have to destroy them.
Here is our roadmap for today. 1. Inside the ionization chamber. 2. The initial ionization event. 3. Which electron gets lost. 4. The radical cation shatters. And 5. The rules of fragmentation. Let's jump right in.
Part 1. Inside the ionization chamber.
Okay, so picture this chamber not as some quiet, sterile laboratory, but as a high-speed, high-energy collision zone. Before a molecule can be analyzed and detected, it has to be converted into a charged particle. Inside this chamber, a filament is heated to several thousand degrees Celsius, which emits a beam of high-energy electrons. This beam acts as a catalyst, violently striking the stream of sample molecules. Now, the energy required to remove an electron from most organic molecules, which is its ionization potential, is usually only between 8 and 15 electron volts. But to acquire reproducible data that we can actually compare against global databases, a standard 70 electron volt beam is used. It is massive overkill. It's literally like using a cannon to open a peanut. And that massive excess energy is exactly what makes the rest of our story so explosive.
Moving on to Part 2. The initial ionization event.
Let's freeze-frame the narrative right at the exact moment of impact. Bam! The electron-molecule collision violently strips away a single electron from our sample molecule, creating the absolute star of our show, the radical cation. Because electrons carry a negative charge, losing one leaves the molecule with a net positive charge. But crucially, it also leaves it with an unpaired electron. This dual chemical nature, being both a radical and a cation at the exact same time, places the molecular ion in a highly excited vibrational state. It is just intensely vibrating with all that massive excess energy transferred from the 70 eV collision.
And this setup brilliantly illustrates the strict rules of physics governing these particles. When that initial molecular ion forms, it's called an odd electron ion. Interestingly, if the original molecule contained no nitrogen, this odd electron ion will actually have an even mass. Later on, when this ion breaks apart, it might form an even electron ion, which totally counterintuitively will have an odd mass. I know it sounds a bit backwards, but these definitions are the absolute foundation for understanding the chemical pathways our molecule is going to take as it flies through the machine.
Part 3. Which electron gets lost?
This brings us to a huge structural question. A typical organic molecule has dozens, maybe even hundreds of electrons. When that beam hits, out of all the electrons in a molecule, which specific one is the casualty? Well, the answer lies in a hierarchy of vulnerability. I want you to think of the molecule's electrons kind of like a Jenga tower. The electrons most likely to be ejected are the ones held least tightly by the molecule, the ones hanging out in the highest potential energy molecular orbitals. Step 1, the non-bonding electrons. These are like the loose pieces sitting right at the very top of the Jenga tower. They are by far the easiest to knock away. Step 2, the pi orbital electrons, like the ones you find in double bonds. They're a bit more structural, sitting right there in the middle of the tower. And step 3, the sigma orbital electrons. These are the single covalent bonds holding the very framework of the molecule together. They are the tightly held foundational blocks at the very bottom, and they are absolutely the hardest to dislodge.
Part 4. The radical cation shatters.
So, we've knocked a crucial piece out of our molecular Jenga tower, and we've pumped it completely full of excess kinetic energy. What happens immediately after that destabilization? Look at this number, 10 to the negative 5th seconds. That is a tiny fraction of a single microsecond. Because the radical cation is in such a highly excited, violently vibrating state, time is of the absolute essence here. If the molecular ion can somehow hold itself together for longer than this incredibly brief window, it gets accelerated through the machine and hits the detector totally intact. But any ion with a lifetime of less than 10 to the negative 5th seconds, it will spontaneously shatter before it can even be accelerated out of the ionization chamber. It literally vibrates itself to pieces right there on the spot.
And finally, Part 5, the rules of fragmentation and structural analysis.
Here is the really beautiful resolution to our micronarrative. When that molecule shatters in the gas phase, it doesn't just turn into random chaotic dust. The shattering of the molecule is actually governed by highly predictable unimolecular chemical rules. Think of it as the instruction manual for a shattering molecule. We've got these fundamental fragmentation processes. There's alpha cleavage, which is initiated by the radical site, where a bond neighboring the radical just snaps. We have inductive cleavage initiated by the charge site, where an electronegative atom pulls an electron pair right toward itself. We even have incredibly complex molecular gymnastics like the retrodials-Alder for unsaturated rings, or the famous McLafferty rearrangement. That's where a hydrogen atom actually reaches across space, transferring to the charge site via a six-membered transition state before the molecule breaks in two. It is just this highly choreographed dance of destruction.
And guiding all of this chemical chaos is Stephenson's rule. It states the most probable fragmentation is the one that leaves the positive charge on the fragment with the lowest ionization energy. What does that mean in simple terms? It means the universe favors stability. The molecule is breaking apart for sure, but it will predictably break to form the most stable carbocation possible. Heavily substituted, highly stable ions will form fast and frequently, and they'll completely dominate the final data we see. It's honestly just like Markovnikov's rule from organic chemistry, but playing out in a gas phase vacuum.
Now let's ground all of this theoretical physics into a visual reality we can actually use for structural analysis. What you are looking at is the actual mass spectrum of cyclopentane. The original intact molecule weighs 70 mass units, and if you look all the way over to the far right, you see that little peak at 70? That is our molecular ion. That's the radical cation that somehow managed to survive longer than 10 to the negative fifth seconds. But look at that massive peak over at 42. That is our base peak. That is the direct result of cyclopentane shattering, losing a neutral molecule of ethene, which weighs 28, and leaving behind a highly stable fragment ion sitting at mass 42. By reading these shattered pieces like a giant puzzle, we can completely reconstruct the original structure of the molecule.
So, I want to leave you with this thought. We just witnessed the highly structured, predictably beautiful rules that govern a molecule's destruction in the very first microsecond of mass spectrometry. If stripping just one single electron in a violent 70 electron-volt collision can literally force a molecule to reveal its entire structural identity, what other secrets are hidden in the spaces between atoms? We are truly just beginning to see the boundless mysteries of the molecular universe. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.